So recently, we have learned kind of a large number of tests for series, and these tests can tell us whether a series converges or diverges. And so we've kind of, I think at this point, we've learned all the ones we're going to learn in this class. And so it's kind of a question of when do you use each one. So I have attempted to address that here. And this is not complete instructions that are going to work all the time. It's kind of impossible to give instructions like that, but this is kind of a good bet. So let me run through it, and I tried to put these in some kind of order, like maybe look for the first thing first, and then if that doesn't work, then look for the second thing. It's kind of impossible to really put this in an order, but well, here goes. So one thing that should always be in the back of your mind is if the terms don't go to zero, then the series diverges, and that's called the test for divergence. So if you see a series and the thing inside just doesn't go to zero as n goes to infinity, then you're done. So that's a good thing to notice right off the bat, so you don't spend your time doing anything else. Of course, you should also recognize a p-series right off the bat. If it's 1 over n to the p, and by the way, if you have any constant on top, it doesn't really need to be a 1. You can directly just use the p-series test. So that's another thing to get out of the way right off the bat. Another thing that can kind of tip you off and send you in a particular direction right away is these powers of -1. They could be -1 to the n, and it doesn't really matter if it's n plus 1 or n minus 1 or n. We also saw an example that was like this. By the way, cosine of pi times n is literally just the same thing as -1 to the n. For even values of n, this gives you +1, just like this. For odd values of n, this gives you -1, just like this. So there are sneaky ways of putting something that's equivalent to -1 to the n. So those come up once in a while, mostly if somebody's trying to trick you. But if I see that, I'm going to do the alternating series test. And this is important to get out of the way because some of the other tests require all of the terms to be positive. So if you've got a lot of positive, like terms alternating between positive and negative, you probably really want to use the alternating series test. Okay, so moving on down the line. If you have a constant to the n, and of course, if this constant happens to be -1, then I would have already done the alternating series test. So let's assume this is like not. I'm not talking about -1 to the n. It's some other constant to the n, typically a positive constant, like 2 to the n, 3 to the n, and stuff like that. So if I see that, also if I see factorials, then I would strongly recommend the ratio test for those. If I don't see that stuff, and what I see is, you could call this an algebraic function, but just to keep the terminology light, I mean powers of n or polynomials. And when I say powers of n, that could include stuff like the square root of n. I count that as a power of n because it's n to the 1/2. So if you have a fraction and everything on the top is like a power of n or a polynomial or square root of n, that type of stuff, and the bottom is similar, then and you don't see this stuff that would have caused you to do the ratio test. So I don't see 2 to the n or n factorial or anything. What I see is just powers of n and polynomials. In that case, I would go to the limit comparison test. And if it's of this form, for the limit comparison test, you have two sequences, and the first one is the original, and the second one is what you get to make up. The second one that you get to make up is going to be a p-series. That's what I mean by we're going to compare this against a p-series. Okay, now the stuff from here on down is kind of like less common. I would say most series that you're going to get in real life or in my class are going to be susceptible to one of the things that we already talked about. These last three get a little bit particular. Of course, for a lot of this advice that I'm giving you, there are multiple things that could work. But I'm trying to avoid giving you like a whole world of possibilities. I'm just going to tell you to go ahead and do something. So anyway, moving along. The next thing I want to talk about is the root test. And this is not something that I use commonly, but there's one situation where it's basically that's the thing to do. If you have a non-constant to the n, then this is definitely a situation for the root test. It doesn't happen often, but when it does, you want the root test. There's also the direct comparison test. This is a test that requires you to have some inequalities between your original, the terms of your original series and another series that you get to make up. And often, so first of all, there's a lot of situations where you can use the direct comparison test, but the limit comparison test works just as well, and so I would use that instead, because the limit comparison test works in a lot more situations. The times when you really need the direct comparison test tend to be times when you have, I would describe it as an obvious inequality, often involving stuff like sine n or cosine n, because there's obvious inequalities here. In particular, sine and cosine are always between -1 and 1. But it could be some other obvious inequality. And the last thing is, the integral test is very nice, but we have learned other tests which are in many situations more powerful than the integral test. And so by the time we've learned all these tests, the integral test is kind of just going to fall to almost a last resort. Sometimes you need it, though. In particular, if you're out of ideas, if nothing else has worked, and just vaguely, if you see something that you could integrate, like the terms of the sequence look like something that you could find the antiderivative of, that's good for the integral test, because you're going to need to do that to apply the integral test. Okay, so let's see some examples. I'm not really going to fully do these series in the sense of tell you the answer. I'll tell you some of them, but I'm not going to show all the work. What I want to focus on is what would you try first? Like just glancing at these series and considering the advice I just gave you, what's a good first line of attack for these? So this first one is exactly what I mean when I say like powers of n / polynomials over powers of n / polynomials. Like square root of n counts as a power of n, that's n to the 1/2. Here I have a polynomial and it's underneath a root, and that's okay too for this. Also, I don't see, like maybe I should have gone through these other things that I don't see. Like, well, actually, let's even talk about this first one. As n goes to infinity, just real quick, this is something that I'm just doing in my head. I'm not even going to write anything down, because as you approach these, there's going to be observations that you make that you don't necessarily write down on the paper. These observations are mostly just motivating us to send us in a particular direction. It's not necessary to like determine the answer, but it's necessary to figure out the fastest way to get the answer. Anyway, as n goes to infinity, the top is like n to the 1/2, And the bottom, I would say, is like n to the 4/3. I say that because n to the 4th is the biggest power in here, so it's like I can cover this lesser stuff with my finger. So the top is like n to the 1/2. The bottom is like n to the 4/3. So the bottom is a larger power than the top, so I would say the terms do go to 0. That's a thought that we can have entirely in our heads just to tell us, let's not bother with the test for divergence, because we just figured out in our heads these terms do go to 0, therefore the test for divergence wouldn't tell us anything. The test for divergence is only good when the terms do not go to 0. Okay, we don't have a p-series. This is not, I mean, it's more complicated than a p-series, but it doesn't simplify down directly to a p-series. It's not alternating. I don't see -1 to the n or any of that stuff. I don't see 2 to the n or 3 to the n. I don't see any factorials. I do see this. So we end up here. So this is going to be limit comparison test, and I will even go one step further and tell you what my b sub n is. In a manner of speaking, we already kind of discussed what b sub n is. This is going to be my a sub n, and my b sub n is going to be like the simplified version of this, which I get by just ignoring the lesser parts. So this is n to the 1/2 over n to the 4/3. And now this is the hardest part. What's 4/3 minus 1/2? That is 8/6 minus 3/6, so n to the 5/6. So this, I'm going to tell you, the answer is going to be that this series diverges. I'm not showing all the work. In particular, for the limit comparison test, you have to show that the limit of your a sub n divided by b sub n is positive and finite in order to determine that this series does the same thing as this series. So I'm skipping that work. But assuming that work works out, I can see that b sub n, like the series with b sub n would be a p series where p is 5/6, so it would be diverging. Anyway, I need to go faster, so let me run through these. What do I see here? Actually, this one might be a little bit hard to just look at and immediately tell right away that the terms go to 0. They do, roughly speaking, if you have the certain intuition. The certain intuition is that exponential growth is really fast, but factorial growth is even faster. So the bottom is going to infinity faster than the top. And by the way, polynomials like nothing compared to any of these. This polynomial is much slower growing than exponential and even slower than factorial. So just roughly speaking, if we have that intuition that the terms do go to 0. And so let's not bother showing that in a formal way, because even if we showed that, it wouldn't tell us anything. If the terms go to 0, then you have to keep trying. It's not a p-series. It's got stuff that p-series shouldn't have, like factorials and exponentials. It's not alternating. It does have constant to the n. It has 2 to the n. It also has n factorial. So ratio test. If you do the ratio test on this, you should find that it converges. I'm going to skip the work, but because I'm just focusing on what direction to go. So that's the direction I would go. What do we have here? Well, first thing I would notice is the -1 to the n. This is alternating series. What do we have here? This is exactly what I mean when I say a non-constant to the nth power. This is exactly what sends us to do the root test. What do we have here? Well, the terms do go to zero. As n goes to infinity, this goes to infinity. Natural log also goes to infinity. So as n goes to infinity, I'm getting 1 over infinity, so the terms do go to zero. So let's not waste our time writing anything down for that because it wouldn't let us draw any conclusion. But the terms do go to zero. Having gotten that thought out of the way, it's not exactly a p-series because I have natural logs. It's not alternating. It's, I don't see 2 to the n or 3 to the n. I don't see any factorials going on. It's also not quite this form because I have the logs. Like, I do have a power of n, like n to the 1 would count as a power of n, but the logs don't fit in here. It isn't like this. It isn't a non-constant to the nth power. I don't see any sine n or cosine n or anything like that. I would do the integral test. And just let me say another quick word about that. When I was describing the integral test and I said this sort of vague comment, something you could integrate, here's what I mean. Imagine replacing the n's with x's. Could you do that antiderivative? If you could, then this is a good indicator that the integral test is a reasonable thing to do. And we could, again, I'm going to be very light on showing all the work, but doing a quick substitution where w is ln x, dw is 1 over x dx, this turns into 1 over w squared dw. So this is something that we would be able to integrate, and seeing that you're not going to have a problem doing that is a good indicator that pursuing the integral test might really tell you something. Okay, last one, and this is, well, maybe I'll go real quick. The terms do go to zero. As n goes to infinity, this cosine squared n doesn't affect much. This is always from 0 to 1, and then this is going to infinity, so this is like a 1 over infinity situation. So the terms do go to zero. As n goes to infinity, this goes to zero. So let's not write anything down for that because it wouldn't let us draw any conclusion. The presence of this cosine squared is going to mean that it's not a lot of these things. Like it's not exactly a p-series. It's not alternating. I don't see a constant to the n or any of this stuff. The presence of this cosine squared means that I'm not just looking at a polynomial or powers of n. I've got a trig function in there. It's not like this. We're here. You probably knew we were going to end up right here. So, direct comparison test, and let me say another word about this. What inequality would we use? In fact, I can write an inequality in either direction here. Let me be careful so I don't make a fool of myself, but let's use this logic that we love to use, which is just if I keep the top of a fraction the same and I make the bottom bigger, that makes the whole fraction smaller. So I can make this bottom bigger. If I make this bottom bigger, that's going to make it smaller, so I'll write this here. I can write n plus 1 because cosine squared is at most 1. Of course, cosine squared is also at least 0, so I can make the bottom of this fraction smaller by just dropping the cosine squared. So what did I just do? I just came up with two inequalities that are both true. Which one's going to be the useful one? Well, there's two ways to use the direct comparison test. Either you find a series with smaller terms that diverges, or you find a series with bigger terms that converges. And so it pays to know which way it's going to go so you don't waste your time. Roughly speaking, when I look at these, well, maybe I'll point to this one first. This is literally a p-series. This is literally a divergent p-series. So this inequality would not let us conclude anything with a direct comparison test, because if the series that I'm wondering about is smaller than a divergent series, that doesn't tell me anything. If it's smaller than a convergent series, then it converges. But if it's smaller than a divergent series, it could go either way. So this inequality would never tell us anything. It's true, but it wouldn't tell us anything. This inequality is what would tell us something. Of course, this isn't exactly a p-series anymore because it's got the n+1, but you could easily tell that this diverges because it essentially behaves like 1 over n. For example, and I'm not going to show all the work, I could use the limit comparison test where this is one of my series and the other series is just 1 over n. And again, skipping the work, not writing anything down. The series that I make out of this, meaning, I chose crazy starting points for all of these. I don't know if you noticed, but just to tell you that n could start anywhere. So anyway, I'll start at 7 because I won't start at 7. But we know for these questions the starting point really doesn't matter since we're just being asked whether the series converges or not. Anyway, this series diverges. I'm just telling you that it does. I'm not showing the work. I mentioned the work. It diverges by the limit comparison test against 1 over n. And therefore, the terms that we are actually being asked about, which are larger than the terms of this series, that means that this series diverges. So the answer to this is going to be that it diverges. Anyway,